Hello, geometry students. This lesson is all about the trapezoid. And there are two different ways you can technically define a trapezoid. One is that it has at least one pair of opposite sides parallel. The other is that it has exactly one pair of opposite sides parallel. I like to go with the second definition. I think it makes it a little bit clearer, but occasionally you might see in different textbooks the first definition. So I just thought I'd throw it out there. So definition of a trapezoid is going to say it's a quadrilateral with exactly one pair of opposite sides parallel. So the sides that are parallel we refer to as the bases. And so I'm going to show those parallel sides and kind of mark them, that these are the bases. And so sometimes you might know formulas where it's base 1, base 2. It doesn't matter. They can be interchanged there, right? And then as for your non-parallel sides, these are sometimes referred to as the legs over here, right? So properties of a trapezoid. Same side interior angles are supplementary. Well, think about in this diagram, if here's parallel lines, if here's your transversal, these right here are same side interior angles. So supplementary just means they're adding up to 180. And since in a trapezoid, you have parallel lines, each of these legs can kind of be treated like a little transversal. So this angle and that angle right there, those should add up to 180. So I can kind of maybe circle those and show it. All right, and then the same argument can be made over here that these guys, this angle, whatever this one is here, and whatever this guy is down here, all right? And maybe I'll mark them, differently here. They add to 180, all right? Something to keep in mind that in a basic old trapezoid, these angles here, like they don't have to be the same. So like this diagram is a perfect example of, oops, sorry, I'm a little crooked there. It can be much more slanted on one side than on the other. It could look like this. And so this could be, a 30-degree angle here. This could be a 70 over here. And that would make this top one 150, because together they have to be 180. That would make this top one 110. So it's just good to kind of note that they definitely don't have to be the same. So sometimes when we think of a trapezoid, what we tend to think of is an isosceles trapezoid. So that's what we're looking at next. But just know that not every trapezoid fits into that category. If it is isosceles, just like an isosceles triangle, that means that the non-parallel legs, or the sides, are congruent. So we can know that those two sides are congruent. So we can say an isosceles, I'm going to abbreviate, trapezoid means that the non-parallel sides, which I said before, sometimes we refer to those as the legs, are congruent. And then just like an isosceles triangle, all the details that come along with it. So since those legs are congruent, you get the base angles congruent, and you would also get the top base angles congruent because of that supplementary relationship. So remember, if this is one of the bases and that's the other one, it's the two angles adjacent to the same base. Right? So over here, I'm going to say an isosceles trapezoid, I'm really abbreviating there, implies two pairs of congruent base angles. That notation should look kind of familiar. It's kind of the notation we used when we did proofs. And those proofs are coming back, just FYI. Not yet, a couple days. And then the last one, when the diagonals are drawn, the diagonals are congruent to one another. So if you have an isosceles trapezoid, the diagonals are congruent. So that means diagonal BD is congruent to CA. And what's probably pretty obvious, but you never know, is that the two little parts are not congruent. So they do not bisect each other. So even though we usually don't write down properties they don't have, sometimes it's good to just clarify that, since in every parallelogram, the diagonals do bisect each other. Here, they do not. All right, flip it on over to the next page. So page 21 in your note packet. So this first part, you just have a bunch of examples. So I hope you have your calculator nearby. It's just asking us to find the measures of some missing angles and missing segments. So the very first one says, find the missing angles in the trapezoid shown below. All right, since it's telling us it's a trapezoid, we can know for sure that, yeah, those are going to be parallel. It's not trying to trick us. So these two have to add to 180. Same with these two. So nothing crazy here. If you want to show work, you can do 180 minus 47, or I can go right to my calculator to do that. So 180 and then minus 47. That'll leave me with 133. Maybe I'll darken up my calculator screen just a little bit. Oops, I'm brightening it. There we go. Okay, now we're on track. So this one is 133 degrees. All right, and then if that's 116, we can go 180 minus 116. That'll leave us with 64 down here. All right. The second one, find the length of JB. So JB is this little segment here, given that KB is 24, and then from M to F is 32, so that full length. All right, well, a couple of things. Without them telling us, you see one pair of parallel sides, the other side's congruent, so we know right off the bat that this is an isosceles trapezoid. So we have to make sure that we're clear about what kind of figure it is before we make any assumptions about it. From there, then, yeah, diagonals have to be congruent. So that means that from F to M is equal to from J to K. And so if FM, if that whole thing is 32, I'll call that piece that we want to know X. That means the whole length from J to K is X plus 24. I can make an equation, but I certainly don't have to. Some of you might have just said, well, can't we just subtract? Well, yeah, absolutely. So 32 minus 24, we're left with 8. So that's the length of JB. So just using those observations there. All right, the next one, you were told that it's an isosceles trapezoid. So that's going to be important here. We can also see these are parallel, so we know it's a trapezoid regardless. Find the measure of all four angles. All right, well, because it's isosceles, that means the base angles are congruent, or you can say equal, either way you want to say it. Right? So they have to be along the same base, which means angle Q and angle S. So let's make an equation out of this. We can set this 2x squared plus 19 equal to 4x squared minus 13. All right. Just like any other problem, we should get our like terms together. So I'm going to move that 2x squared over. And at the same time, just to save myself a little bit of space here, I'm going to add 13 to the other side. So I get 2x squared. That's going to give me a total of 32. And then from here, right, to get that x alone, divide by 2. And then we can take the square root. Now, when we solve it this way, one little trick step that you got to remember from probably Algebra 1 is that when we go in and take the square root ourselves, you need to remember the answer is going to be plus or minus. So this is technically plus or minus 4 right there. All right. A different way to have done the same thing, you can even just watch, you don't necessarily have to write it down, is that when we got to this step, we could have said, well, if 2x squared equals 32, we could have subtracted the 32 over and then factored. So this would have came down with a GCF of 2, and then this is difference of squares, x minus 4, x plus 4. And you can see right here how this would have produced 4. This one would have produced negative 4. So I know I'm kind of smushing it in there, but just good stuff to recall from Algebra 1. All right, regardless of how you get those two answers, it says find the measure of all four angles. So when we come back over here, angle Q and angle S are supposed to be the same thing. So you can plug into either one. So if I plug in positive or negative 4, I'm going to kind of go like that. The reason I can get away with that is the first thing you're going to do is square it. If I square positive 4, 16, square negative 4, it's 16. So either way, I get 2 times 16 or 32. And then we're just adding 19 on there. And so if we add 19, let's say 32 plus 19, that'll bring us up to 51. All right, so in the picture, this angle's 51 degrees. This angle has to also be 51 degrees. And then to find the other ones, we can use the idea that those are supplementary. So 180 minus 51, that's going to leave us with 129 degrees for angle P and for angle T. Awesome. All right. Haven't done much factoring, so that's a nice little blast from the past there. All right, for number 4, you've got the diagram where ABCD is a parallelogram. They're telling us AB is parallel to DC. All right, so we can mark that. AD is congruent to BC. Ooh, all right, congruent. That means we've got an isosceles trapezoid here. Angle A is 4x plus 20. Angle C is 3x minus 15. What is the measure of angle D? All right. What you are expected to take away from this is that we have congruent base angles. So angle D is the same as angle C. So I can label this guy then 3x minus 15. Angle A and angle B are the same. So if I wanted, I could label this. So I could add all of them, set them equal to 360, or I can use a pair that I know are going to be supplementary, like angle A and angle D. So I can add them together and set them equal to 180. So 4x plus 20 plus 3x minus 15 equals 180 degrees there. All right, combine all your like terms, we get 7x. That's going to give us plus 5 equals 180, and then keep on going. Subtract the 5 over, and then divide. You might be mental mathing it. You might be like, I'll grab my calculator here. That's up to you. But if we divide, what we should get there is a nice clean 25. Always makes us feel good when we get nice whole numbers. All right, and then the last part, measure of angle D. So we know it's 3x minus 15, so it's just 3 times 25 minus 15. Well, that's going to be 75 minus 15. That'll leave us with 60. So that's the measure of that angle right here. All right, we have one last new thing to talk about in today's notes. So flip on over to page 22 of your packet. You slide back down here, and that is called the trapezoid mid-segment theorem. There's also a triangle mid-segment theorem, and we'll talk about that later. But the trapezoid mid-segment theorem, first of all, what's a mid-segment? Right, well, it is exactly what it sounds like. The mid part of it is the fact that it's connecting the midpoints of the two sides of the trapezoid. And the specific sides it's connecting are the two legs. So let's write that down first, that the mid segment is the segment connecting the midpoints of the legs, which just means the non-parallel sides of a trapezoid. So it's the segment connecting the midpoints of the legs of a trapezoid, right? It's got some properties that can happen here. Something that might even just look correct here is the fact that the mid-segment ends up being parallel to the bases. So the bases we know were already parallel, that segment will also be parallel. So the mid-segment, all right, is parallel to the bases of the trapezoid. And then the last part where we bring in a little bit of algebraic work is the idea that the mid-segment is actually equal to the average of the lengths of the bases, right? And so think about how you average anything, or specifically two numbers. We would add them together and then divide by 2. So it's going to be equal to base 1 plus base 2 divided by 2. So think of this as base 1, and we can call that guy base 2. If we average those values, that's going to give us the length of the mid-segment. Mm-hmm. So that's the little formula we want to use to be able to solve some of these problems. So for number 1, when it says find the length of EF, well, I've got a trapezoid. That is the midpoint over here. Those two parts are congruent, so that's a midpoint here. So this is definitely a mid-segment, which is kind of important to take note of. So then we can simply say that the mid-segment is equal to 13.5 plus 8 divided by 2. That's it. All right, on your calculator, make sure, add together the numerator, get a single value, then hit divided by 2, or use that alpha y equals. I can remind you guys of that. If I go alpha y equals, and then you can make it a fraction, that would be fine too. All right. Otherwise, if you don't do it like that, and you just do 13.5 plus 8 divided by 2, your calculator only divides the 8 by 2. So you get the wrong answer. Just letting you know that. All right. For one like number 2, this one's giving you slightly different information. They're giving you the mid-segment length. So this part is the mid-segment. What we don't know is the length of EH. I'm going to call that X. Okay. So in that regard, if I think about the formula, the mid-segment is equal to base 1 plus base 2 over 2, kind of shorthanding here. We know the mid-segment. We can plug that in on the left. I'm going to call that guy base 1, so we know 25. What we're looking for then is base 2. And I'm just going to put an X in there, just because it makes it a little easier than writing B2. From here, think about how you'd solve this. We would get rid of that 2 by multiplying it on over. And so 16.5 times 2, we'd get 33. And that's equal to 25 plus X. And then just subtract the 25 over. So minus 25, there you go. That's got to be the length of that other base. Now, something that is good to take note of as well is that because it's the average, it means that it's equally distant from the lengths of the other two. Okay, what the heck do I mean by that? Well, if I grab my calculator and find the difference from 25 to 16.5, there's a difference of 8.5 between those two values. All right, 16.5 minus 8, that's also a difference of 8.5. So something that we could have done, which is it's a less algebraic way to do it, is to figure out what's the difference from the base to the mid segment, and then subtract that same difference to get this. Right? So still works, but it only works if you have numerical values. If I have something like example 3, where I have variables as the lengths, it's not quite as easy to make that work. Not saying you couldn't, but I would say in that case, go back to the formula. So for one like this, if here's base 1, here's base 2, and then this guy is my mid segment, when I say go back to the formula, I would plug everything in to this. Base 1 plus base 2 over 2 equals the mid segment here. All right, so let's show it. It would be n plus 6 equals base 1, n plus 3, plus base 2, 3n minus 5, all over 2. All right. To solve that, we do the same thing we did last time. We would multiply both sides by 2. Remember, when you do that, you're going to distribute. So that's going to be 2n plus 12. Those 2's would cancel. And now I can clean up everything over here as I bring it down. So n and 3n would give me 4n. Plus 3 minus 5 would give me minus 2. And then you should be able to solve from here. Right here, I want you to finish this up. This is the post-video question. So you should be able to find the value of n, and then it's really asking you to find the length of the mid segment. So what does that come out to be? All right, finish that up, go answer that question. Thanks for watching, guys.